to cover the chapter 5 of our book. This chapter is about the 5 reservoir fluids. We want to know what type of reservoirs we have based on the characteristics or the phase behavior of the fluids that we have discussed earlier. So we started with chapter 1 when we looked at the different structure of the hydrocarbon and non-hydrocarbon fluids. And then we moved to chapter 2 when we studied the phase behavior, like pressure temperature relationship and pressure volume relationship of the pure components. And then we studied this behavior for mixture of two components and then the multiple components. And then in chapter 3, we started developing the equation of a state for ideal gas. And then we corrected that for real gas and introducing the compressibility equation of a state. Then we moved in chapter 4, where we basically introduced more equations of a state that has been used in the industry, like Penn-Robinson equation of a state, which is very famous in the oil and gas industry. But here in this chapter, what we are going to do is we're going to look at the behavior of the different mixtures based on their based on the phase behavior. The good thing is the phase behavior of a multiple components are very similar to the phase behavior of the mixture of two components. Okay, so there is a very good similarity that we can use that to study their behavior. Okay, so here basically what you have is a pressure versus temperature diagram of a mixture of ethane and N-heptane. Okay, so ethane being the lightest component. Usually remember the lightest components, they are always in the left side. So they have a much smaller range of the temperature. Okay, but as the molecules becomes heavier, they go to the right. They are basically covering higher range of temperatures. Basically their critical temperature goes up. So as we have heavier and heavier molecules, the critical temperature starts going up. So if I'm looking at the phase envelopes, so this is the number 1 is 100% ethane. So it has a very small phase, very small, type of two-phase region and two-phase line. In this case, since it's pure, and then it's all in the left side. But as we go to the N-heptane, which is a heavier component, it lays down. Now, if I start mixing these two components, this was a discussion we had before in chapter 2. Depending on how much of which component is added, then the phase behavior or the phase envelope, okay, tends to shift toward that component. For example, here the phase envelope number 2 includes 90% of ethane and only 10% of heptane. So this phase envelope is more toward the left side. It's more toward the lighter component. And as we add more and more of the heptane, where like in case number 9 or number 6, let's say, we have almost 90% of component and heptane. So the phase envelope is basically laying down toward this. So the way it works is the more lighter component you have, the phase envelope will shift to the left and it becomes smaller. It covers a small range of temperature. The maximum temperature of the envelope, if you remember, we defined that as a Criconden term, becomes less. And as we add more and more heavy components, this phase envelope will shift to the right and the maximum temperature of the envelope or the Criconden term becomes larger and larger. So having a heavier component, heavier hydrocarbon, the envelope tends to lay down on the temperature axis, and having less, it just shrinks and goes to the left. So if I have multiple phase envelopes like this, and this behavior is very similar when you go to the multi-component, okay? So if you have multiple phase envelopes, by simply looking at the behavior of those, the one which is larger and has a higher Criconden term, that one definitely has a heavy component, so it's most probably an oil reservoir. And as it shrinks and it comes to the left and becomes smaller, then that's most probably represents the gas reservoir. Okay, so this is a qualitative way of identifying the petroleum fluids. And we know as we go to the left, we will have more of a light component, so we will have more of a volatile components into our oil, into our system. So if I want to rank these phase envelopes based on the volatility, So the one which is more into the left is more volatile than the ones which are basically to the right hand side or laying down on the temperature axis. Okay. There are different ways of identifying the type of reservoir fluids we have. The most accurate way is to just take a sample and send it to the lab. Okay, and in the laboratory we can do different tests. We can come up with the exact properties and type of the fluid. Okay, but this is kind of expensive and time consuming, and you need to just make sure that what type of samples you are taking. If the sample should be taken at the reservoir condition. So if you take a sample from the reservoir condition and then seal it. Usually we do it with the canister cell that preserves the pressure and temperature. And then when we send it, we send it to the lab for the experiments. But as I said, this is kind of expensive and it's more time consuming. There are other ways of figuring out what type of reservoir fluid we have at the reservoir, and one is just monitoring the initial producing gas oil ratio. So when we open a well, at the first time, so remember this works when you have a brand new reservoir. Okay, you cannot just pick a reservoir which has been producing for 10 years and then you say, okay, I'm going to look at the gas oil ratio and just based on that define what type of reservoir fluid I have. No, it has to be the original gas in place. Okay, so initial gas oil ratio. So when we open the well and then we start producing the gas and oil, the amount of gas we are producing at the surface divided by amount of oil we are producing at the surface. So we measure that. We know how much oil we are producing and how much gas we are producing. That ratio gives us some indication of what type of reservoir fluid we have. Okay, but sometimes this is not very accurate. Sometimes there might be some overlaps. Okay, so the next thing is to look at the stock tank oil gravity. Okay, we are looking at the oil that we are collecting and we are looking at the density of that. In the oil and gas industry, instead of density, we are using the API gravity, okay, which we will go over it. So the API gravity has a relationship to the specific gravity of the oil. And the specific gravity is simply the density of oil normalized by density of water. So based on different API of oil that we are collecting, we can also come up with the idea of what type of reservoir fluid we have, okay? And we can also look at the color of the oil, okay, that we are collecting. That also gives us some indication. But generally speaking, we have 5 different type of reservoir. Okay, we have black oil reservoir, we have volatile oil reservoir, retrograde gas, wet gas, and dry gas. Okay, so black oil includes more of the heavy components. Okay, so it's a higher density, higher viscosity oil. Volatile oil, as the name says, has more of a volatile component, more of a lighter component, more of a propane, butane, pentane, hexane. Okay. So it's lighter. So if I look at that graph, how the phase envelope will shift. In the case of black oil, I'm expecting a very, very big phase envelope with very high cryo-condensate term. Okay, the phase envelope lays down on the temperature axis. As I go to the volatile oil, I expect this phase envelope to shrink and the cryo-condensate term to decrease. Then I go to the retrograde gas. I expect this to shrink more. So the retrograde gas, so I have a black oil reservoir, volatile oil reservoir. These two are oil reservoirs. And then I have three different type of gas reservoirs. So in the case of black oil, as I said, it's heavy, high viscosity. Then I have volatile oil. And then in the case of retrograde gas, what I have is a gas reservoir. But this gas reservoir has a potential to produce liquid. Okay, it can produce liquid at the reservoir condition, or it can produce or at the surface. Okay, so there is a possibility of producing liquid at the reservoir. Originally, at the initial pressure, that's all gas. But when you start producing from these reservoirs, you start dropping the pressure. So what happens if you don't understand this really well, and if you don't know what you're doing in your operation condition, you might start losing all those volatile components at the reservoir. So you are basically losing them. They're not going to come to the surface, so you're not producing and you cannot sell them. Okay, and it's not just you're losing that benefit of the volatile components. You're also damaging your reservoir because you are just leaving droplets of the liquid everywhere in the reservoir. That's going to block the flow paths for the gas. Okay. The next type of reservoir fluid is a wet gas reservoir. So in the case of wet gas reservoir, again, at the initial condition, you have gas. But this gas can only produce liquid at the surface. So you don't worry about the operation. You know this wet gas reservoir cannot leave any liquid at the reservoir condition. The only way that you can get the liquid out of this gas is when you bring that at the surface condition. Okay, and then the easiest reservoir fluid is the dry gas. So the dry gas is the most probably more than 95%, 90% methane, and this reservoir produces gas only, and it doesn't matter at the reservoir condition or at the surface. The only thing that you can get out of it is gas, most probably methane. So and some ethane. So this reservoir will not produce any liquid at the reservoir or at the surface. That's the easiest reservoir to deal with. Okay. So now we are going to study the behavior of every one of these reservoir fluids. So starting with the black oil reservoir, as I said, the initial gas oil ratio could be a good indication. So if I start producing from a reservoir and I see the amount of gas I'm producing over the amount of oil I'm producing is less than 2,000 standard cubic feet of gas per stock tank barrel of oil, that's most probably a black oil reservoir. Why? Because you don't have that much of light components. Everything is heavy. The amount of gas you're producing compared to the amount of oil is not much. So if the gas oil ratio is less than 2,000, that's basically the black oil reservoir. As I said, we also measure the density. So if I look at the density of the stock tank oil, and as I said, we are usually looking at the API gravity instead of density. So the API gravity, this equation, again, we need to memorize that, is equal to 141.5 divided by specific gravity of oil minus 131.5. And a specific gravity of oil, as I said, is the density of oil divided by density of water, okay, which is 62.37 pound per cubic feet, okay. So if I have the density of oil, I divide that by density of water, I get the specific gravity, I plug into this equation, and I get the API gravity. So if the API gravity of the oil turns out to be less than 45, then that could be also an indication of having the black oil. And as the name says, this is, if you look at the oil, it's very dark. It's often black, okay? The other property that we can measure and is what we call formation volume factor, okay? So the laboratory analysis indicate an initial oil formation volume factor of less than 2 for these black oil reservoirs, okay? So what is the initial, what is the formation volume factor? That's the ratio of the volume of oil at the reservoir condition over the volume of oil at the standard condition. So if I have 1 barrel of oil at the reservoir condition, how many barrels of oil I can get at the surface? So you always get less amount of oil at the surface, okay? So 1 barrel of oil cannot produce 1 barrel of oil at the surface. In the case of black oil reservoirs, the initial formation volume factor is less than 2, okay? So basically, like you get a little bit more than half of the oil that you are producing, okay, at the surface. And if I look at the analysis of these reservoirs, these black oil reservoirs, these are like they usually have more than 20% of heptane plus, so more than 20% of heavy component, which indicates large quantity of heavy or non-volatile hydrocarbons in this fluid. Okay, so initial gas oil ratio less than 2,000, API gravity less than 45, formation volume factor less than 2, and more than 20% of heptane plus. These are good, and the black color of the oil. These are good indication. So we look at these. Sometimes like the API gravity might overlap with different reservoir fluids, but if we compare the list of the parameters that we have, we can easily identify the fluid type. If I look at the phase envelope of this black oil reservoir, as I said, it's a huge, large phase envelope. The Crichton term, or the maximum temperature, is very big. One other property is these isovolumes. So these isovolume lines, they basically show the amount of liquid. So at point 1, you are all liquid. So again, as I said, this is a critical point. To the left we have oil, to the right we have gas. So this reservoir condition is somehow falling on the left side of the critical point. And as we produce, we hit the dew point at the constant temperature, and we go to the two-phase region. And as you can see, these isovolumes that shows the amount of liquid are evenly distributed. this is another indication. So if I look at the phase envelope and it's huge and I see evenly distributed the isovolume and the critical point is on the left hand side, far away the critical point, that's definitely my black hole reservoir. Okay, so in the next slide, in the next part, we are going to talk about the volatile oil and its properties.